The last video of this thermodynamics unit is intended to kind of introduce and start to build some skills in a unit we will deal with later. Unit 9 is the Applications of Thermodynamics unit. It gets into when, how, and why we would use additional principles of thermodynamics. So sometimes Unit 6 would be called thermochemistry. It focuses on heat flow. It focuses on enthalpy. It focuses on temperature change. But if we stop right there, it's not always clear why a reaction might be endo or exothermic, yet still a very favorable process or a reaction. For example, exothermic reactions hopefully would make sense as a reaction that would be likely to occur. They have more than enough heat themselves or reaction or energy to continue once they have started, and they would release energy to the surroundings. Endothermic, on the other hand, require heat. There are lots of cases where an endothermic process can happen. If there's sufficient heat in the surroundings, that energy can be absorbed and the process can occur. The challenge is when and how do we know that there is sufficient energy? So, to go beyond just heat, there are two other main concepts. One is entropy, or a measure of randomness and disorder. When processes occur, the energy doesn't only stay as heat. The energy doesn't only stay as kinetic or potential energy. Some of that energy is dispersed or is sent into a state that can't be used. There are connections with the enthalpy change of the surroundings, the temperature, and entropy. But for our purposes, when we're looking at entropy of a system, it is just how randomly or are the particles arranged. As I change states from solid to liquid solutions to gases, or as I change from one scenario, a pure substance maybe to a mixture, I am taking an orderly system and making it disorderly. That process requires no outside energy or no outside intervention. Things favorably or naturally become more random as long as we allow that process to run. The universe expands, your bedroom gets dirty on its own, and things mix together when they're in the same container. If we had a brand new bag of M&Ms that we opened, we wouldn't expect it to be sectioned off into each separate color. Even if that's how they got placed into the bag, over time, they randomly mix together. That doesn't just happen with M&Ms or with the socks that hide under your bed in your room. That happens with all particles because of their random motion. So entropy is a big part of understanding how energy is transferred to a less usable state. Heat is usable. Kinetic energy is usable. It changes the properties of the system or the surroundings. The entropy is that random loss of energy, that more dispersed state of it. And when we describe energy, we also need to understand that entropy is something that can make a reaction favorable or not. We can calculate it by looking at the entropy or the randomness of our products compared to our reactants in terms of quantitative values, or we can compare it in terms of qualitative values to say, are we starting more or less orderly than we're ending? We will connect this with some of our thermodynamics labs now, and we will apply it again later. But the key idea is thinking about, are the things arranged more randomly at the end than they were at the beginning? This comes together with enthalpy in a concept called Gibbs free energy. Gibbs free energy is the application of the second law of thermodynamics. It says that anything which is favorable, meaning anything that happens on its own, or anything that happens without the outside input of energy, increases the entropy of the universe. When we are studying a chemical change, a physical change, a state change, we often study just the one system we're looking at, not the universe as a whole. But when that change happens, it transfers some energy to or from the surroundings, and those surroundings obviously are part of the larger universe as a whole. When we are changing the temperature of our surroundings, we are changing the entropy of the surroundings. The particles are maybe moving faster or slower as a result. When we are releasing heat or taking heat from the surroundings, we are changing the way that the energy is dispersed. Increasing the randomness of the universe is the natural flow of energy. And the only time that we would see a system go against that natural flow of energy is if we have a heat or an entropy change for our system that is actually more favorable. What we will see here is really something that we can do math with, we can do conceptual things with later, but we just want to understand that entropy is not the end of the story. Some reactions, in fact, many reactions are exothermic. They release energy, and that is a favorable flow of energy, not just for the system, but for the surroundings. The system has more energy than it needs, or more than enough energy such that it adds it to the surroundings. It does not require energy from the surroundings in order to occur. Some reactions become more random or become more disorderly or increase the entropy as we go. One chemical breaking into two, for example, water breaking into hydrogen and oxygen, breaks us into more smaller pieces, into more random arrangements, into more entropy. That process increases the entropy of the overall system as well. And when we have a reaction that meets both of those qualifications, thinking about endo or exothermic, but also judging the entropy and randomness, that's how we can know which reactions occur and we can explain why they occur. So for now, we just want to be aware that enthalpy is an important part of the thermodynamic explanation and an important part of the discussion of energy. But the dispersal of energy in the form of entropy and the combination of enthalpy and entropy together into Gibbs free energy is a key to understanding and applying why some reactions occur while others don't, while some reactions are very favorable and others only occur in special conditions, and why some things do not occur at all without being forced to occur or without the input of energy from an outside source.